And on page 21, you should find this problem, finding the cherry starbursts. A bag of starburst candies can be considered an SRS, a simple random sample, of the whole population of starburst candies. Since there are 4 flavors, the probability that each starburst is cherry flavor is 1/4, or 0.25. Each bag of starburst contains 200 candies. Suppose we buy 1 bag of starburst. We're going to let X represent the number of cherry flavor starburst candies in the bag. And I would like for you guys to answer the questions on this page all the way down to the bottom where it says normal approximation to the binomial. What? Yeah, we skipped a couple pages. Yep. It's the pages that we're skipping is like review problems of combining random variables. But I want you guys to do all of page 21. We're going to take somewhere between 7 and 10 minutes. If everybody's finished up at 7 minutes, we'll go over it at 7 minutes. If it takes a little bit longer, we can give up to 10 minutes before we go through this. You are allowed to use your notes. You are allowed to work with each other, and you will need a graphing calculator for this. So take a couple minutes. Please make sure that you are using proper notation at every point. Is it? Don't just assume. Don't just assume.
One bag doesn't change. I mean, it's not saying you're choosing strawberries, that each strawberry in the bag
Cherry.
Cherry. It's the same thing. Strawberry and cherry
Are you
basically the
disagreeing?
same thing.
I mean,
No, she's agreeing because it. No, she's not agreeing.
Bro.
No, it makes sense though, right?
Isn't there a strawberry Starburst though? Yeah, you can't even say it's
But
the
it
same
makes sense
thing.
though, right? Because it's just how many cherries are there inside the bag.
You're not taking one
Yeah,
out.
you're not taking one out, so. What?
I wasn't disagreeing.
We were disagreeing with you on the cherry.
That's what it
It
says.
doesn't say. It doesn't, a bag of strawberries, therefore says there's a probability that each Starburst is cherry. They only buy one bag of strawberries.
Why did
It
you
doesn't say
take
anything
the
about
strawberry?
it,
Why
but
did you
that-
take the
I don't want
strawberry?
That's a later problem for a
This
later.
is true, but if you are trying to determine whether or not it is binomial, you
Yeah.
cannot approach it from this idea that an untouched bag. Because in that case, every situation would be independent if we're not touching the bag.
Oh my god. So it is independent, so
If you
it's not
take the bag,
independent.
it's poured out and you're like,
Oh, weird. So
how
it's,
is it?
how
Don't
would
do bad. It's, what are we getting
no,
on
we
this
have
class?
some, we have some, wait, no.
Wait,
what? What are you talking about?
I know what.
So, how did we know we were talking about the skills?
The 10%. It's like there are so many that it doesn't matter. But
How did we check the
It's bits.
that's a great question. I thought it was like the probability of choosing
Yeah, like, if,
there. With taking a random sample without replacement of the size n from population n is less than or equal to 0.1.
And so what is n?
125, which is greater. No,
Two
n
hundred.
200.
And it's 200. Because it said that the bag of Starburst, the bag of Starburst altogether could be considered a random sample from the population. What would the population be?
It's 200 stuff.
I don't have a number for it, but I can still define it.
all the
A
Starburst.
lot.
All the Starburst.
All the Starburst. Again, I don't have a number for it, but I can define it as being all the Starburst. So do you think the 10% condition is met?
Yes. You guys would choose.
Because why?
All
Show me my
Starburst.
graph.
Let me give myself some.
200 is less than or equal to.
Less than. I think it's just less than.
It's less than or equal to.
It is?
Less than or equal to 10% population.
10% out of all the Starburst.
You gotta define your population.
All starters.
Yes. Got about 4 more minutes to work. If you need help, please let me know. I'm happy to help.
Yes, but you have to define
It's not independent, but due to the 10% condition, it's still.
Hey, so I'm right.
I'll accept.
Okay.
No, guys, because my original thought was it's not independent. So then you convinced me that it was. Yeah,
It's not.
Yeah, if you redo it, I would absolutely give you.
It's-
I apologize.
Technically.
My error. I normally double check that.
Wouldn't it be defined as independent because
On
it
the bottom
follows
paper,
the
that's
10%
6
rule?
No,
on the bottom.
it's not independent, but because it shows statistically in.
So it is independent.
No, it's not independent.
But it,
So
It's
So
statistically.
technically speaking, it's not independent. However, because it meets the 10% condition, it is,
Still by
it's
review.
independent enough for our circumstances. So we can check off and we can say, yes, it's independent, even though it's technically not independent. It is so close to being independent because the probabilities aren't changing very much as we like. If I go and buy 5 bags of Starburst, taking those 5 bags out of the whole population doesn't dramatically change the proportion of cherry to lemon to strawberry to orange. That's the other flavor. I can't remember the other flavor. Thank you, Jerry.
Yeah.
See you tomorrow.
Coming.
Average cherry. Some probability of success.
Average cherry starburst in a
I
bag
realized
is
the
50.
entire
It's the average number of cherry starbursts.
This looks right. I don't remember that. This.
No, it does. Amount sounds better. It's grammatically correct. Or quantity. How's that like that?
Just say number. The average
I
number.
already changed my number. Yeah, I already changed it to amount. Average amount of cherry.
I don't remember the formula for the final.
Oh, so then, okay.
You're welcome.
It's 50.
I feel like I have to sneeze.
Which one are you stuck on?
Oh, I just don't remember the formula to find the standard deviation.
Oh, to find standard deviation.
Oh, yeah.
Yep, and you have that on your formula sheet. You don't have to memorize that. You do get that on the formula sheet. Okay, 0.75 to what power? It should come out to be a whole number. Oh, yes, it is, because it is a whole number. That's this. So that means that doesn't go in that way, 51 places. So it's better to write it down like this, rather than try to then change it into a whole number.
Like you had that.
200. All right. Let's see how we're doing. Is this a binomial distribution? Yes, this is a binomial distribution. So that means we should be able to define what success and failure are. What's success here? Pull in a cherry flavor. Failure would be not cherry. Independence.
Yes, 10% condition.
I'm going to say technically no, but 10% condition. So if we're going to say that we have the 10% condition met, you actually then have to show that to me. So what is little n? What is our sample size? 200. So 200 is less than or equal to 0.10 times my population. What's my population? Yep, total number of starbursts are all starbursts. And then little n fixed number of trials would be what? Not 20, 200. 200. What is the same probability of success, our p? 0.25. So yes, this is a binomial random variable. We said yes, x is a binomial distribution with n equal to 200 and p equal to 0.25. When you define something as being binomial, you have to tell me what n and p are. If you decide that a certain situation is geometric, then you would still need to tell me what p is. But geometric would not have a fixed number of trials. Why does geometric not have a fixed number of trials? Yes, because it's trials until success. We're going to keep going, keep going, keep going until we succeed. So it's not a fixed number of trials. All right, number 2, n and p. We already answered this. What is n? 200 and p? 0.25. What is the mean of x? 50. How do we calculate the mean? Yep, n times p, so 200 times 0.25. How would we interpret that then? After many, many, many trials, which in this case would be 200, so after many, many, many bags of 200 starbursts, like we keep going and buying bags and buying bags and buying bags, What?
Cherry flavored Starburst is close to 50.
The number of cherry flavored Starburst in a bag of 200 after many, many, many bags of 200 Starburst is 50 cherry Starburst in the long run.
The after many, many, many is the mandatory part, right? Beside, of course, the...
I mean, you want to use the word average in there somewhere.
Yeah, average.
Yes, so the average Starbursts, the average number of Starbursts, or you could say there is an average of 50 cherry Starbursts in the long run after many, many, many bags of 200 Starburst. You could word it like that also. Yes. What do you mean? This is not geometric. So you start off by defining what kind of random variable it is, and then once you know what the random variable is, you will apply the formula for that random variable. Yes. And you have the formulas that are labeled on your formula sheet. This is the formula for the mean of geometric. This is the formula for the standard deviation of geometric. This is the formula for the mean of binomial. This is the formula for the standard deviation of binomial. They are labeled on your formula page. All right, number 4, what is the standard deviation of x? Yes, 6.124, which we get by doing the square root of n times p times 1 minus p. So the square root of 200 times 0.25 times 0.75 is how we got 6.124. What does that mean? What does the standard deviation of 6.124 mean?
The average Starburst varies by 6.124 from the mean of 50.
Yes, typically the number of cherry Starbursts in a bag of 200 is going to vary by 6.124 Starbursts from the mean of 50 Starbursts. What'd you say? Approximately 6.124. Yes, you could use the word approximately. You still want to get typically varies in there. Those two words are going to be really important when we are interpreting standard deviation, because the standard deviation is, this is about how far off we are usually. That's what standard deviation is conveying. What is the probability of getting exactly 60 cherry flavored Starbursts? How do I need to start both my work and my answer here? What does the beginning of this need to look like? P, yes. I'm asking for a probability. So we need to start with a P and parentheses. What goes inside the parentheses? X equals 60, yes. Because remember, my random variable x is how many cherry Starbursts there are. So the probability that x equals 60 equals, what comes next? Parentheses, double decker, what's inside them? 200 on top, 60 on bottom. Number of trials on top, number of successes that we want to see on the bottom. What comes after that double decker parentheses? 0.25 to the power of 60, probability of success, to the power of the number of successes that we want. Then what? Yes, 0.75 to the power of 140. This is 200 minus 60, because that's our number of failures. Okay, this first part up here, the 200 over 60. I want you guys to recognize this, because again, this is how you would see it on a multiple choice problem. But how do we actually put that into the calculator? 200C60, like this right here. And how do we get to this on the calculator? Math. And then you arrow over to probability. And your answer at the end, I got 0.0171. 0.0171 when I typed that into my calculator. If that is not what you got, then double check. What's the difference between 5 and 6? It says at most, which is going to be what? less than or equal to. So we're going to do the probability that x is less than or equal to 60. Do we do this the same way as number 5?
No.
No. What do I use to do this one? Binom CDF. What do we have to feed into binom CDF? Trials, probability, and X. It's like successes. That much. That would be our upper boundary. You could think of it as our upper boundary. So what's our trials? 200. Probability? 0.25. And my upper boundary, X? 60. And that comes out to be what? I got 0.955. So a little bit more than a 95%, almost 96% probability that if you reach into this bag of Starburst, that you are going to get at most 60 Starbursts. So basically opening the whole bag of Starburst on the ground. How many did we get total in the bag? Chances are it's going to be 60 or less cherry-flavored Starburst. Last part of the question, the normal approximation to the binomial. So we already know that we met our 10% condition because we had to talk about that with it being binary. Or sorry, with it being binomial, rather. If we are going to use a normal approximation to the binomial, we have to meet our large counts condition. N times p has to be greater than or equal to 10. Is that true? Yeah, because n times p was what? 50. So n times p is 50, and then we have to do n times 1 minus p. That needs to come out to be bigger than 10, or the same as. What would that one come out to? What would we get when we do n times 1 minus p?
200 times 0.75.
Yep, 200 times 0.75. What is 200 times 0.75? 150. So that means my normal approximation is appropriate. N times p was greater than or equal to 10. N times 1 minus p was also greater than or equal to 10. When I do n times p and n times 1 minus p, this, n times p, plus this, n times 1 minus p, should add up to be whatever n is. Notice my 50 and my 150 add up to 200, which is our sample size. All right, so we're going to do a normal approximation. That means I need a picture. What's the mean that goes right down the center? 50. Then we need a big capital N off to the side with what two numbers in it? 6.124. And where's my boundary line going to be? At 60. And then shaded which way?
Left.
Shaded left. So it should look kind of like this. So then we do normal CDF. So probability that x is less than or equal to 60, normal CDF. Lower bound would be something stupid small. Would 0 be an okay lower boundary here?
Yeah.
Yes. In this scenario, 0 would be an okay lower boundary. Upper boundary has to be 60, mean of 50, standard deviation of 6.124. And what do we get? What do we get? Yep, 0.949 or 0.95 would be fine. What do you notice about when we calculated the exact probability on number 6 and when we did our normal approximation?
They're pretty close.
They're pretty close together. They're pretty close together. All right. Nicely done. What questions do you guys still have about binomial distributions or the normal approximation to the binomial before we go over to your other yellow packet?
Okay. On the test, it's for your test. How should we be writing number 5? And then how should we be writing it on the AP Stats test?
Okay, so if this was short answer question, a free response style question, I need to see this for sure. This would count as your work and then your answer. So when you are writing work for me, those are the pieces that I need to see. If it's a multiple choice question, this will be one of the answer choices. So you don't have to write that one down for me, but you need to understand that this is the same thing as this, and it's how we calculate this.
So should we be writing it with the double-decker bus fraction?
I would look at this and make sure I know how to write it so that I know how to recognize it.
So if we write that, that's fine.
If you write this and then you jump right to here for the answer, that's fine. That's fine. This is how you put it into the calculator, but as long as you know how to get from here to here, I don't care which one I see.
Okay.
Yep. Does that help?
Yes.
Okay. What other questions, comments, or clarifications do you guys have about this before we go on to your other yellow packet? All right, let's switch gears then and get out that AP Stats fact sheet. We're going to flip to chapter 6, which is just one page. It's page 8. Chapter 6, we talked about random variables. We had 2 types of random variables that we talked about. We had discrete when we did discrete random variables, binomial falls under this. Geometric falls under this. And when we just have the tables that are giving us a probability distribution. So that was discrete. Then we also had continuous. The continuous random variables that we looked at in this chapter were normal and uniform. Random variables will always be quantitative that describe the outcome of a chance event. The probability distribution will always be between 1 and 0, with it totaling to 1. Remember, that means the area underneath the curve. If I look at the entire area, the area will always be 1. Expected value, which is the mean. When we have a table, this is how you will calculate the expected value. You take the probability of outcome number 1, and we multiply it by the value of outcome number 1. And then we do the same thing for outcome 2. We take the value times the probability. We do the same thing for outcome 3, value times the probability. and we add them all up. Remember that sigma, that uppercase sigma means to add everything up. So you're going to add up all of these products, value times probability. For the standard deviation, you need to use lists, and then you do one variable stats with L1 and L2. I did not make you calculate standard deviation by hand. The formula is included on the formula sheet, but you can use the graphing calculator for standard deviation. You do not have to calculate that one by hand. So you put in list 1 and list 2, you put your values and your probabilities, and then you push stat and you go over to calc, and you want one variable stats. All right, binomial random variables. Make sure that it is binary, independent, or 10% condition. If it's not fully independent, if it's not with replacement, then you check your 10% condition. Number of trials is set. So you could say n equals, and the probability of success, p equals. You must write down when you have a binomial random variable. You have to write down, this is binomial. If it says, how is the random variable distributed? You would say binomial with, and then tell me what n is equal and p is equal to. If you have written down bins, B-I-N-S, to check on the side, and that's where you wrote what n is equal to and what p is equal to, that would be fine. Geometric random variables still has to be binary, still need our independence, so we can use 10% for that as well. Trials until success, and then our probability of success would be p. And so again, if you think something is a geometric random variable and you are asked how it is distributed, you would say geometric. You would not have n equals, because we do not have a set value of n for geometric, but we do have a set value of p. All right. Bottom part, or middle part actually. When we want to do exact for binomial, this is where we have n and k times p to the value of k times 1 minus p to the value of n minus k. This is how we calculate the probability that something is exact. So i.e., the probability that x equals 5, we might have 20 over 5 times 0.2 to the 5th power times 0.8 to the 15th power. Binom CDF, this is when we do a less than or equal to. Less than or equal to, where p is the probability, n is the number of trials, and x is the value or the upper boundary. So the probability that x is less than or equal to 5 would be binom CDF 20, 0.20, and 5 with things labeled N, that didn't show up very well, N, P, and X. The mean of the binomial distribution is N times P. Remember, mean is the same thing as expected value. Standard deviation is the square root of N times P times 1 minus P. You get those formulas on the formula page. Remember, I showed you guys last week, it's going to be right in the center of that first page inside a table. When we want to do exact with geometric, we do 1 minus P to the value of K minus 1 times P to the first power. So the probability that X equals 5, I would do 0.8 to the fourth power times 0.2. That is for geometric for exact. Geometric CDF is where we want less than or equal to. Bring this down here. If I wanted the probability that X is less than or equal to 5 for a geometric random variable, it'd be geomet CDF. We don't put N in, but we do put P in, and we put X in. Where X would be my upper boundary. Mean for geometric distribution is 1 over P. That is the expected value. And the standard deviation is the square root of the probability of failure divided by the probability of success. So the square root of 1 minus P divided by P.
And that's just square root the numerator, not the denominator.
Correct. It is only square rooting the numerator, not the denominator. Which, if we had more time, I could get into why that is. There is a mathematical reason for that. But we didn't have time in this chapter to get into the nitty-gritty of why that is. Down at the bottom, we have all the interpretations. I'm not going to take the time to read all of the interpretations. We've talked about them many times. This would be a great place to go to practice. One of the things that I did want to get down at the bottom of the page, though, is if we have a greater than or a greater than or equal to or a less than but not a less than or equal to, how we would split that up. So if I wanted to do the probability that X is greater than or equal to 10, probability that X is greater than or equal to 10, I would need to do 1 minus the probability that X is less than or equal to what? 9. If I wanted to do the probability that x is greater than 7, that would be 1 minus the probability that x is less than or equal to what? 7. And if I wanted the probability that x is less than 13, that would be the same as the probability that x is less than or equal to what? No, you were closer the first time. 12. When we have a greater than or a greater than or equal to, that's when we have to do the 1 minus. If it is a less than, then we can simply rewrite it as a less than or equal to. Sometimes it's helpful to write out a little bit of a number line to understand why your number would change versus when it wouldn't. This is for our discrete random variable situations. So tables, binomials, and geometrics. Very specifically with binomials and geometrics. Is there anything else that you guys wanted to make sure that we get written down in this section about random variables? You guys have a little bit less than 15 minutes of class time remaining. Homework is due tomorrow. I am happy to answer questions that you guys might have about the homework, but that is what I would like for the remainder of this class time to be spent on, is working on the homework that is due tomorrow. Huh?
It's due tomorrow.
No, I want you to start it today. At least look at it today.
All right.